And I'd like to welcome the last speaker of the session, Alexandru Cojocaru, who will talk about quantum lifting for invertible permutations and ideal ciphers.
Yeah, thank you so much. So in this presentation, I'll be talking about our work on quantum lifting for invertible permutations and ideal ciphers. And this is a joint work with my amazing collaborators, Minki Han, Chupeng Liu, Takashi Yamakawa, and Aram Yun. So in this presentation, we are going to work in this query model, which is this well-known elegant abstraction widely used in both cryptography and complexity theory. And the most famous example is the random oracle, in which several crypto systems are designed and analyzed. And in this model, we are saying that a query algorithm is trying to solve a particular problem by just querying a black box function, as you can see here. And the complexity of this algorithm is given solely by the number of queries performed to this black box function. However, as you know, quantum computing is bringing a new query model, the quantum random oracle, in which now superposition queries to this black box function f are allowed. And as a result, this is equipping quantum parties and, more importantly, quantum adversaries with more powerful capabilities. And an even further extension of these models occurs when this black box function f is a permutation. And in this case, we say we are dealing with the quantum random permutation oracle, where now superposition queries to both the permutation and to its inverse are allowed. So the main ideal goal of this work would be trying to relay the security of a cryptographic scheme against classical adversaries with its security against quantum adversaries. And more precisely, ideally, we would like to have a lifting theorem that would say something of the following form: that if we have a cryptographic scheme or a security game that is secure against classical attacks, then we can also lift it to ensure its security against quantum adversaries. And more concretely, in this work, we are going to focus on establishing lifting theorems for the security of search games in the quantum random permutation oracle model. So a bit more concretely, the setting that we are going to focus on today can be summarized as follows. We have a challenger that can perform up to k classical queries to a permutation and to its inverse. And we have a quantum adversary that can perform up to q quantum queries to the random permutation and to its inverse. Moreover, the adversary and the challenger are also allowed to exchange classical communication. And at the end of the protocol, the challenger is either going to accept or reject. And we say the adversary has won this game if it resulted in the challenger accepting. So this notion of lifting theorem was introduced originally by Yamakawa and Zandri as a tool that enables lifting security from the classical random oracle to the quantum random oracle. And at the high level, the result that I'm going to refer on from now on as YZ states that if we have a security search game that in which the challenger only needs to perform a constant number of queries to the random oracle, and this game is secure against the classical adversary, then this game also becomes secure against the quantum adversary, so in the quantum random oracle. And a bit more concretely, the result states that if the challenger in such a security game performs key classical queries, and an arbitrary adversary making q quantum queries can win this game with probability epsilon, then one can also construct a classical algorithm that only needs to perform key classical queries. So notice the same number of queries as the challenger, that can win the security game with probability at least epsilon divided by 2q plus 1 to the power of 2k. So in this work, the main result would be establishing similar lifting theorems, but in the quantum random permutation model and the quantum ideal cipher model. And at this point, you may wonder, why are these lifting theorems useful? Because at a high level, they essentially tell us that if we want to study the security of a cryptographic scheme or a security game against an arbitrary adversary, well, it actually just suffices to study its security against an adversary that only needs to perform a small fixed number of classical queries. So a bit more concretely, in this work, we are going to work in these two models, the query permutation model, in which every part, including the adversary, has access to a permutation and to its inverse, for a uniform random permutation. And secondly, the ideal cipher model, in which we are saying that every party has access to a parameterized function ek and to its inverse, where each ek you should think of it as being an independent random permutation. And why these two models? Well, because as we know, several constructions and proofs are developed in the random permutation and ideal cipher model. And just to mention some very famous examples, this includes Ibn Mansur, Davies-Meyer, and sponge construction. But at this point, it might be worth highlighting the distinction between the quantum random oracle and the quantum random permutation, and more precisely, why is it so more challenging to work in the latter. So on one hand, random functions have this very nice property of perfect independence. Namely, if you look at the outputs of a random function, these are going to be pairwise independent. On the other hand, if you look at the outputs of a random permutation, these are going to be almost independent. But it is exactly these weak correlations between the outputs that invalidate all the methods we have in the quantum random oracle. And this issue of these weak correlations occurs even when the algorithm or the adversary has access only to the forward permutation. But as we have seen in the definition of the two models, in these two models, the algorithm or the adversary has access to both the permutation and to the backward permutation, so to its inverse, which destroys its independence, making it extremely challenging to extend all these proofs in the random oracle. Okay, so as mentioned, the main first result is establishing a lifting theorem in the quantum random permutation model. And at the high level, this lifting theorem says the following. Suppose we have a challenger that performs k classical queries to a permutation and to its inverse, and then for any quantum adversary that makes q quantum queries to the permutation and to its inverse, we can construct another classical adversary that only needs to make k classical queries. So again, the same number of the queries as the challenger, that can win this security search game with probability, at least the probability of the arbitrary adversary A, divided by this quantity over here. And sort of like wanted to emphasize again the main takeaway message. This is going to be particularly useful because now, as we said, if we just want to cite the security against an arbitrary adversary, well, this lifting theorem suggests that it's sufficient to cite the security against an adversary that performs a small fixed number of classical queries. So now I want to mention some applications of these lifting theorems. So on one hand, we can use it to derive some new quantum query complexity bounds, but of course we can also use it to derive some post-quantum security results. And on one hand, we can use it to show some tight bounds for the quantum hardness of the double-sided zero search game that I'm going to define in a second. But we can also use it to show the post-quantum security for properties such as preimage resistance, one-wayness, or collision resistance for constant round sponge, but also for the collision resistance of Davies-Meyer. So now let's revisit these applications in a bit more details. So if we now look at the double-sided zero search game problem, so in this problem we are given a random permutation that acts on two n-bit strings and its inverse. And the task is to find a pair xy such that pi of x is equal to y, and moreover x and y must have at least n leading zeros. And now if we directly plug in this problem into our quantum lifting theorem, then it is quite clear that k is equal to 1 because the challenger only needs to make one query to verify the solution of the algorithm. And then therefore it just suffices to study the hardness of this problem against an adversary that performs a single classical query. And for such an adversary, it's quite clear that it can win this game with probability at most 2 divided by 2 to the n, which comes from two possibilities. Either this algorithm manages to query a valid pair, or it just simply caresses guesses 1 without querying. And therefore, by applying our lifting theorem, we can directly determine this bound in a very straightforward way, that for any algorithm equipped with Q quantum queries, it can win this double-sided zero search game with probability at the most Q squared divided by 2 to the n, which we also know it's a tight result due to this work of Caroline and Poremba. But moreover, we can also easily generalize it to any game GR parameterized by some arbitrary relation R, where the task is to find the pair XY in this relation. And similarly, by directly applying our lifting theorem, we can show that for any algorithm equipped with Q quantum queries, the probability of winning this game is going to be at most Q squared multiplied by the probability of finding this pair in an arbitrary relation when given one single classical query, which we also know it's a tight bound due to Grover search. But as mentioned, we can also use this lifting theorem to derive the post-quantum security for different cryptographic tasks. And in particular, we can use it for sponge construction, which is this very famous permutation-based hashing function. And here I wanted to mention a bit the history against the history of the security of this sponge construction. So on one hand, we know that in the classical world, this is as secure as the random oracle, but in the quantum world, not that much is known. So in particular, what we know is that a single round sponge satisfies preimage resistance and one-wayness, as well as resetting differentiability in certain parameter regimes. But prior to our work, no results were known about multi-round sponge. And it turns out that by directly applying our lifting theorem, we can reduce the post-quantum security of the classical security of sponge. And this, in turn, allows us to derive some non-trivial bounds for constant round sponge, namely for properties such as preimage resistance, one-wayness, and multi-collision resistance. And here, I should mention that a very beautiful work of Alexandru, Majens, and Tokat also showed quantum differentiability for multi-round sponge, but via a very different route. And secondly, we can also use it for the security of Davies-Meyer and PGV hash functions, which is this famous block cipher hashing algorithm underlying SHA-1, SHA-2, and MD5. And a similar story happens here. So in the classical world, we know that it is one-wayness. It is one-way and collision resistant in the ideal cipher model. But in the quantum world, only one-wayness was proven, while collision resistance was still open. And similarly, by directly applying our lifting theorem, we can show that Davies-Meyer is collision resistant in the quantum ideal cipher model. And of course, our analysis is not specific to Davies-Meyer. We can also apply it to other PGV hash functions. Now, in the remaining minutes, I wanted to mention a bit about the tools we use to show this. So here I just want to introduce this notation for reprogram oracle, namely that this is a new function that on input x is going to output y, and on any other input is just going to behave as the original oracle. So this is this notation when you'll see it from now on. So now it is going to be worth re-mentioning the YZ lifting theorem to give some intuition about our new result. And to do this, we are going to focus on this function inversion task, which is simply asking to find the preimage of 0 for the random oracle. So here, we can think that such a query algorithm, there are only two possibilities. So suppose this algorithm is going to output X star as a solution for this problem. Then either this X star was queried by or X star was never queried. And we can denote by I star the index of the query at which X star has been queried by I, and we say that I star is both if X star has never been queried. Then the crucial observation in YZ that allowed them to derive the lifting theorem was that A cannot distinguish between the following two situations. So in the first situation, A has oracle access to the reprogrammed oracle on the outcome X star from the very beginning for all its queries. And in the second case, A has oracle access to the original oracle up to the point of querying X star, and then to the reprogrammed oracle. And this allowed the YZ to define a simulator that essentially simulates the output of A having oracle access to the reprogrammed oracle. But unfortunately, this very nice and natural approach fails even in the classical random permutation model. Why is that? Well, let's again revisit this double-sided search problem. So similarly, if we use the exact same simulator as in YZ, we would like to argue that the simulator is essentially able to behave similarly to the output of A, having oracle access to the reprogrammed permutation. But this is going to fail due to the inherent dependencies that are inside all these permutations. So what do I mean by this? Well, consider this scenario. Consider the scenario that the simulator is able to guess correctly the index of the query at which the outcome has been queried. But there can still be a situation that a previous query is resulting in exactly the reprogrammed value. So what do I mean by this? It is possible that under the original permutation, a previous query x prime resulted exactly in the reprogrammed value pi star of x star. But then notice that in this case, the reprogrammed function is not even going to be a permutation anymore. And why is that? Well, because we have a collision. And moreover, A is able to detect these inconsistencies. In particular, A notices that there are two different queries, x prime and x, that produce the same output, which contradicts the entire injective structure. And of course, this issue becomes way worse when A has oracle access to both the permutation and to its inverse. So to deal with this, we are simply going to do this reprogramming in a more careful way. In particular, we need to pay some special attention to some special type of queries. So we denote x a hit query if x is going to be equal to the outcome of the algorithm. And we denote by x a miss query if it's going to be exactly the situation of the collision. Namely, if x under the original permutation is going to be equal to the reprogrammed outcome. And therefore, what our task is going to be is to reprogram the permutation, but at the same time maintain injectivity. So in particular, when we do this reprogramming, we also need to take into account this special type of queries. So if x is a hit query, then we're simply going to output the reprogrammed value, pi star of x star. But on the other hand, if x is going to be a miss, to still maintain injectivity, we are going to output the original permutation evaluate to the outcome of the algorithm, so pi of x star. And otherwise, we are simply going to respond with the original permutation. So just to kind of like summarize, we saw that if we just hardcode this rule, then we are violating the injectivity of the permutation. So therefore, our solution to maintain injectivity was to reprogram both the hit and the miss queries. And of course, similar reprogrammings will have to be done for backward queries, but with uglier rules. So what was kind of like our solution? So the simulator not only needs to guess the index at which the outcome has been queried, but also is going to guess if this query corresponds to a hit or a miss. And by defining this type of queries, we are essentially capturing the first query that touches the outcome x star. That can only happen that either by querying the hit or the miss queries. And with this idea in the classical setting, we can also generalize it to the quantum setting with not too much extra work. And this is going to result in a novel measure and reprogram for the quantum random permutation model. And to just kind of like summarize what is this lemma saying. So if we are given two permutations and an arbitrary algorithm A, then we can construct a simulator that, given oracle access to the A and the permutations, is able to simulate the output of A, having oracle access to the reprogrammed permutation. And the success probability of the simulator is going to be at least the success probability of the A with oracle access to the reprogrammed permutation divided by 8q plus 1 to the power of 2k. Just to kind of like conclude, so we have seen a lifting theorem for the security in the quantum random permutation, but also in the ideal cipher model. And we've seen a couple of applications, both in complexity and also in post-quantum security. And here I just want to mention some possible future directions, extending this to some NISQ settings and getting tighter results to show the optimality for other applications. And with this, I would like to conclude. Thank you.
Thank you very much. Are there any questions for Alexandru? Well, let me start then. So I guess Yamakawa and Zandri, it has like two parts. Like you generalize one part to the random permutation case. I was wondering, do you get immediately the generalization of the separation result by considering truncations of the random permutation?
Yeah, so essentially, as you said, they're kind of like these two parts. Yeah, so as you said, they're like exactly these two parts. So on one hand, in our case, what we are doing is we are defining a lifting theorem in the classical case, which is kind of like needed even for the intuition to go to the quantum lifting. And then to kind of like build this, we also need to introduce this measure and reprogram in the permutation case. So I'm not exactly sure if it is possible to get the same result in a slightly different way, but at least I think we follow a pretty natural path to get these lifting results.
Oh, I was meaning that here you basically, this is the lifting theorem for a challenger that makes a constant number of queries and for search games. But I guess in Yamakawa and Zandri, there's also a separation result between the QROM and the ROM.
Yeah.
So I was wondering whether that can be easily bootstrapped to the for the permutation setting.
Yeah. So actually, the constant part here is mostly when you talk about, like, for instance, the sponge construction. Our results apply for like an arbitrary number of queries. But the question is, like, when do we get some tight results? So we do get like a tight result for like double-sided search game, and that is applicable for any number of queries of the algorithm. So we are not bounded at all. But then where the restriction comes is that in certain cases, as the sponge construction, we don't get like meaningful post-quantum security results unless the number of rounds is constant. So in kind of like that sense, we are a bit limited, that we are not able to say that, okay, for any number of rounds, we can show the security. But our lifting and our measurement program are applicable for any number of quantum queries.
Right. Thanks. Are there any other questions? Okay, if not, then let's thank all the speakers of this session.